All right, so now that we know how to find horizontal asymptotes, let's work on finding vertical asymptotes. And vertical asymptotes are actually easier to find than horizontal asymptotes, I think, because usually it works just like finding the domain of the rational function. So in this first example, r of x, we're just going to take, we're going to look at the rational function first of all and make sure it's reduced. Make sure it doesn't have any common factors, and it doesn't. So we're just going to take x minus 5. And instead of setting it not equal to 0, we're going to set it equal to 0. And so we get that x equals 5. That is our vertical asymptote. Okay, let's look at the graph of that. So here's our graph and the vertical asymptote we found. And you can see that as x gets closer to 5 on either side, our graph starts to blow up, right? We tend to head towards positive infinity from the right and negative infinity from the left. So we're never actually going to cross that line x equals 5, but we're going to get as close to it as possible. Now let's try our next example. Here we have a quadratic in the denominator, so we need to factor it to make sure we are reduced. So this guy's going to factor to x plus 5, x minus 2, so we don't have any common factors. So we just need to set x plus 5, x minus 2 equal to 0. And we get that x equals negative 5 and x equals 2. So in the case of horizontal asymptotes, our horizontal asymptote was unique for rational functions, but vertical asymptotes are non-unique, so we're going to have 2. Let's take a look at the graph. So as you can see, we have 2 vertical asymptotes, two places where the graph blows up. And if we zoom out along the y-axis, you can see that we're getting very, very close to both the line x equals 2 and the line x equals negative 5. And you can also see that we have a horizontal asymptote at y equals 0, and that's because the degree of our numerator is 1 and the degree of our denominator is 2. So that's just a little review of horizontal asymptotes from last time. So this last guy, let's go ahead and factor the denominator as well. We can also factor the numerator just to be 100% sure. It factors as x plus the square root of 2 times x minus the square root of 2, and that's just because it's the difference of squares. And we're going to put that over x times x squared plus 1. Now, you might notice that we have a quadratic term here, and you may want to factor it some more. But we actually can't, because x squared plus 1 is never 0. So we can't factor it because that would give us 2 zeros, and we know we don't have any. So we're just going to set these two guys equal to 0 separately. We have x equals 0, x squared plus 1 equals 0. And x squared equals 0, or x equals 0, that's already simplified. That gives us a vertical asymptote. If we try to solve for x over here, we get x squared equals negative 1. And then if we tried to take the square root, we would get x equals plus or minus the square root of negative 1. And we are currently in the real world. We're not talking about complex numbers, so that guy doesn't exist. So we're only going to have one vertical asymptote here at x equals 0. So here's our graph of that rational function. You can see we only have one vertical asymptote. And then you can see that we have x-intercepts at negative root 2 over here and positive root 2 over here. All right, so one more example of just finding horizontal or vertical asymptotes, and then we're going to put this all together. So this last example is just to show why it's so important for a rational function to be reduced. So r of x equals x plus 1 over x squared minus 1. Let's start by finding the domain. So we need x squared minus 1 to not equal 0, so that x squared should not equal 1, so that x can't be plus or minus 1, right? So that's just the set of all x such that x is not equal to plus or minus 1. That's our domain. But now I can rewrite r of x as x plus 1 over x plus 1 times x minus 1. And now I can go ahead and cancel the x plus 1 in the numerator and the denominator, as long as I remind myself that x is not allowed to be negative 1. Of course, x also isn't allowed to be positive 1, but the denominator tells us that. We don't need to specify it separately. All right, so now our only vertical asymptote is what happens when x equals 1. All right, so let's go ahead and graph that guy to see what's going on. All right, so now here's a graph of our rational function x plus 1 over x squared minus 1, and it's really hard to find a computer program that will actually demonstrate what's going on. Remember, we're not supposed to be defined at x equals -1 over here. And what that means is we actually have what's called a whole discontinuity, where there's actually a break in the graph right there. So this guy is called a whole discontinuity, which is spelled like this. Sorry, my pen is not as good on this program. But what that means is you just have an open dot without anything inside. That's how you indicate that. So if you have a term that cancels in the numerator and denominator, so that you don't have a vertical asymptote at that point, you need to make sure that you indicate that on your graph this way.